Yeah, so here, this was on a test last term when I was trying to, remember I had two proof methods, right? The one proof method was, you say if there's a path, then it has this property. So you take the path and you break it down into its parts, subpaths, and you prove it has the property. And then the other way, if it has this property, then we can break it into substrings and we can build a path. Remember that? And here, this example we could do, because look, it has nice pieces. But as soon as you have loops, we're not going to be able to do it. And that's why I abandoned it. So I'm pretty sure that the proof that I gave them when I say last term, I really mean the last term I taught this. I don't know when that was. Sometime in the past, right? And now we're going to, I replaced it with the proof that you're going to have to be able to do. I'll tell you right now, you're going to have to be able to do this. I'll tell you right now, you're going to have to be able to do this. All right? So, this one, right, we have this machine, and it's kind of an ugly machine, right? And somewhat, what happens even more in 3101 is that during the test, people see something like that, and they say they don't understand it, and they panic, and they drown, right? And I really try to focus on how to keep following the steps when you don't understand everything, right? Like the guy like you're like, how do I know when I get the 3? Well, I don't know how to get to 3. I just trust them at 3. Trust that you're at 3 and move forward. All right? So let's see if we can do this, right? I mean, you might say, well, we should be able to do this without proving anything. Well, one, it's nice to be able to prove things. And two, you will have to be able to, I give you a machine like this, and you're going to have to tell me what the machine does. Well, in order to know what this state does, you need to know what all the states do. Right? So that's what we're going to try to do, is we're going to try to figure out what this machine does. All right? So we want to come up with the definition of L, which we don't have yet, and prove that this machine, the language of this machine, is the L that we have in mind. And where we're going to do it is we're going to talk about a set M for each. Oh, by the way, if you weren't in the yesterday, I've changed the notation. When we taught this before the week, I used L here and I used L prime here, and I changed it to M and L. Why? Because here I want to focus on, we're talking about the machine, and here we're talking about properties of languages. All right? So I'm going to define these two things. All right? So first we're going to talk, there are going to be two different worlds. There's going to be a divide line here. First we're going to talk about the machine and paths in the machine and labeled each path has labels along it, right? And so we're going to talk about MQI for state QI will be the set of all strings such that there's a path to state QI labeled with this string alpha. Right? Everybody got that? And over here we're talking about languages and properties. So what's that? Here for each state QI, we're going to talk about some set of strings with some property. All right? And our goal is to prove that for each state, these two sets are the same. All right? And so the way I would do it, in fact, this is exactly what I was saying in 3101 a few minutes ago. Right? Start with a concrete example and see if you can understand it. All right? So somewhere by random, I come up with a concrete string, and let's trace it out and think about what it does and what do I want to remember about it. Right? What do I want to remember when I'm in this state? Well, what do I want to remember about this substring? What does Pooh write on his blackboard? What's common about this string? Right? So this is a dumb string. It doesn't have A's and B's in it. Somebody clearly copied this slide from somewhere else. All right? So this string here has no meaning whatsoever. All right? But anyway, that's the idea. We can think about strings and what they do. All right? So here I'm going to just give you answers here. I'm going to tell you what I think is true about each of these states and see if you can agree with me. All right? The first state, who gets there? Oh, I haven't taught you about, I don't know why that one's an E and this one's an epsilon, but this is an epsilon transition, and I haven't told you about them yet because we're so far behind. But an epsilon transition is if you're an NFA, then suppose the next character to read is a 1, and there are a bunch of arrows leading 1, and a bunch of arrows leading epsilons. Now I have a choice, right? And hopefully I have a fairy godmother to help me. I can either read this 1 and follow one of these arrows, or I could follow this arrow and not read the 1, and then I could follow another epsilon and not read the 1, and then I read the 1. Right? And why do we have them? It just helps us build these machines. And one of the things I like about it, I have one test in which I say, describe this machine to me, and when you're describing this machine, be sure to use the word commit. Right? What does commitment mean to you? It means you get married, you can't back down. You're not supposed to get divorced. Right? That's what commit means. So the moral of that is, don't get married. All right? But here, what have I done by going here or here? I've committed. Right? I've chosen whether to go this way or this way. Right? All right, so here, how can you get here? Well, you can only get here by starting here, and that's the empty string, right? Okay, how can you get to state 1? Well, one thing that's nice about this is you never can come back, right? It's just a path, right? So you come here. Well, I can read anything here, right? Everybody see that? I can get anything. And how can I get here to 2? Oh, and what I did is I split 2 into 2 pieces, because you'll see the nice thing about it is you kind of commit going from the first half to the second half, right? Once you get there, you can't come back, right? Because all these arrows are coming in, right? So here, the first half, you have, what do I mean by Q prime is you've gotten to Q the first time and you haven't done any A's yet, right? So there's a commitment here, right? This here is I'm here, I commit to go over there, right? So if you're here, what do you know? Well, either I ended a B or I haven't seen anything, right? Now, how do I get here? I'm doing a little different thing. I'm changing not only changing my end state, I'm changing my start state. So what happens if I started here and ended here? What do I know I get? What do I get? I get a block of A's, at least one A, right? Here I'm coming back to here. I go around here and I end here, right? And I go at least once. Then I get a block of 0 or more length, even length, right? It could be 0, right? Going from here to here, it could be 0, or it could be even number of A's. Everybody buy that? All right. Now, what about if I start here and I end here? It's the same, except I have an odd number of A's, right? I'm just understanding piece at a time. Yeah? Is it something we've said already? Okay, what is it? Yeah, these? So I've taken this 2 and I've separated into these pieces, right? And why I separated them is to get from one piece to the other, you follow an epsilon transition, so you're kind of committing. And the reason I did that is it helped me understand this machine. Because really, this machine is I'm doing this part, and then I never can go back to this part, right? So it just helps me focus on what happened till I got here versus the future, right? So if you split the state here, when I came here, I either got nothing or I got a string ending in B's, right? And when you say, okay, how do I, and then I can never go back. So how do I get from here to here? Well, I can't go back. So I go around and around. What I get is I get a block of A's. And how many A's do I have? Well, it could be 0 or it could be an even number. Well, 0 is an even number. I just stuck that in to make sure that we know what we're talking about, right? No, if we, here we're coming back to 2. Yeah. This one here is, I did the same just a second ago. So right, so here, to get to 3, you do an odd number, right? All right, so now, what's this is, all strings that can end up in 2, right? Well, you can do anything at the beginning, either, right, here let me read what it says. It ends in a block of 0 of an even length, and that length would be 0, right? Is that true here? Well, this is a block of even A's, and what comes before that block of even A's, right? We want to say, yes, we want to know the length of the block. So what comes before a block of A's? It's either a B or it's the empty string, right? That's what can go before a block of A's, right? Does that make sense? If this is going to be my block of A's, what goes before it? Any string followed by a B or the empty string, right? Does that make sense? All right, so what do we got up to here? We got a block to end, right? But we want to go over to 3. So 3 is a little easier, right? Anything that gets to 3 ends in a block, an actual block of A's, and it has an odd number of A's. Right? Everybody buy that? That's 3. And now what about 4? Well, what do we add on? We add on at least 1 B. Right? So if you go over to 4, it ends in a non-zero block of B's. Right? It's ending in these B's. But the previous block of A's has an odd length. Right? Everybody getting this? Right? So we started with a machine that we didn't know what it meant, but we built something up. Right? So, I guess I could have been pushing buttons all the time, but that would have helped. Sorry, I forgot I did this. It must have been late at night. Okay, I get PowerPoint slide at, itchy. All right, so now, when do we accept? We accept when we're here or here, right? So we accept either it ends in a block of A's that's of odd length, or it ends in a block of B's but the previous block of A's. So what we're saying, it's the last non-empty block of A's has an odd length, right? It might end in a block of B's. And we did this yesterday, and there was a student, who was struggling. It was because it's an English thing, right? And it's an English thing. You have to know the difference between the last block of A's versus the last block of A's. How is all our non-English speaking people doing with that, right? The last block, right? Here, let's say A, B, B. What are blocks? It's continue the same letter. Here, the last block is the B's, right? This is the last block of A's, right? The last block of A's has odd length, right? What about here? The last block of A's has odd length. That's what we're accepting. Everybody buy that? So, I'm going to give you a machine like this, and you're going to have to figure it out. Or I give you, Either way, I give you a thing and you have to build a machine. And this one is kind of easy because it doesn't have cycles, right? When you have cycles, then you're going to have to guess more, right? It requires more creativity to figure out what this thing does. But hopefully I'm giving you an example that's not too hard, right? Let's get out of that, right? So now I could ask you, give me a regular expression, right? And we did this last class, right? Last tutorial, yesterday. So let's not spend too much time on it. Here, the first bit. What's the first bit? This is any string, right? Here's any string. Here's any string ending in a B, right? This is the empty string. So what's this? This is any string ending in B or the empty string, right? What's this? This is an A, so you have at least one A, and then R times, we're going to spew out two A's. So how many A's are we going to have? 2 times R plus 1. Odd. This is an odd number of A's. And then what do we have over here? Any number of B's. It could be empty. That's what we got there. Everybody buy that? Yeah? Here? Oh, so it's kind of like times. I could do this, right? Or I could do this, or I could do this, and it's the same. Right? Why do we do that? Because, right, here it's concatenating between letters, right? Anyway, it's pretty common notation. Everybody follow that? Yeah? No. Good question. To get the 4, you need a B. But we're accepting here or here, right? So we're accepting 0 B's or more B's, right? So here's another question. Why didn't I just put a loop of B's here? What happens if I get rid of this and put a loop of B's? Then it would be 0 or more B's. Then you could get an A again, right? It's all about commitment, right? It's all about marriage again. You come down here, you're committing that we're doing B's from now on. Right? Does that make sense? Oh, long conversion. There's a really, really scary proof that makes me tired thinking about it, that will take that and mechanically compiling it into this, and you haven't learned it, and I'm telling you don't do it. All right? Yeah? At your 4, then you die. If you put a loop here, then you can get an A and come this way. Right? All right, so let's review about NFAs versus these are DFAs. Right? DFAs, every state has one edge for every character. Right? So this is not, because coming out of 4, there's no A's. Right? And also this is not because it has these epsilons transitions. But it's not that NFA-like, right? We could convert this into a DFA pretty easily, right? By putting, could everybody do that? You just put dead states. That's how you deal with the edges not coming out. And how do you deal with the epsilons? Well, I don't know, we could deal with the epsilons, right? But yeah?
After you get into state 3, you have at least 1 A, right?
Into state 3?
Yeah, you have 1 A.
You have an A already.
You have an A already.
Yeah, that's this A.
How about after that A, you follow by 1 A? In that case,
You're here, and you reject. If you get two A's, you ended up in state 2, and state 2 is a rejection. Right? This, yeah, here clearly, yeah. Yeah. I got a new program at one point to make pictures, and I couldn't figure out how to make epsilons. And then I figured it out. So pre-new program, I have epsilons. Post figuring out I have epsilons. There was a period in life where I had E's. That's the truth. Everybody good with that? Yeah?
Can you help me clarify one thing? In the expression, the last B with the star, this means 0
or more.
So, but in the graph, we have at least, you must have at least one B. Right?
No, because we could stay at 3.
Oh, okay.
All right, everybody good?
We can finish by there.
Yeah, so it's because we accept here or we accept here, right? The reason we have the 2 is because we want, when you get a B, you can never get A's again. Yep, excellent. All right, so now, so we did that. Oh, here's just, I narrowed it down to the states that we care about. And now, this is something else I might want you to do on a test. Right? And so I'm starting to get sick and it's 2 in the morning, so what do? I do the silliest things. I put these lines in. And you think those lines are silly, but it takes a while to put them in. All right, so here, what is this saying? Here we can now focus on what we want to prove. So maybe we did it on the previous slide. Let's go see the previous slide. Here. Oh, no, previous slide. No, there's no previous slide. What are we trying to prove here? We're trying to say what we want to prove. Yep, slide's definitely gone. I spent too much time making lines and not enough time making your slides are there. All right, so here, loop invariant T, right? This is like we're proving by induction, and this is our induction hypothesis. It's going to say for all states I, for all alpha of length T, alpha is an M of Qi if and only if alpha is in L Qi. Right? Our goal is to prove that for every state and for every string, these sets are equal. Right? This string is in this. This string has a path if and only if it has this meaning. Right? With an if and only if. Right? And what this is doing is it's shrinking it down to just strings of length T. All right? So we're going to prove this by induction. So for the base case, if we just worry about the empty string, where can you get to the empty string? You can get here, here, or here with the empty string. Right? Empty string, M of this, M of this, M of this has the empty string. Everybody see that? So which of these have the empty string? That has the empty string, that has the empty string, and actually this has the empty string, right? Because the empty string ends in a block of 0 A's, right? So we proved, and these other guys don't contain the empty string, right? Because it's an odd number of A's. Right? Everybody buy that? All right, so now let's, by way of induction, assume that this is true. And our goal is to prove it for t plus 1. All right? So how we do that is a first-order logic thing. We say, give me an arbitrary state. Right? Well, my arbitrary state is Q2. All right? Give me an arbitrary string of length t plus 1. My arbitrary string is alpha c. Why? Because alpha has length t and c has length 1. Right? Everybody buy that? All right, now I want to prove alpha c is in here if and only if alpha c is in here. All right? So up here you got alpha c is in there, and down here you have alpha c is in there. Right? Yeah? Yeah, so if I was mean, I'd make you do them all, but we have a time-limited thing, so I'm going to give you a state. This is all hypothetical, even though the test is at the printers. I would say I probably would make you define all of these sets, and you need them anyway in order, because they're all true of length t in order to prove they're of length that 1 for t plus 1, right?
Are we to give them the sets? Because what if I know how to do the if and only if proof, but my set is wrong?
Then it won't work. If your sets are wrong, your proof will be wrong. And then you'll say, oh, look, my proof is wrong. Oh, maybe that's because my set's wrong. Oh, I better go change my set. Right? All right, so you get these sets. All right, everybody got it what we're doing? We know that all of these are true for strings up to length t. And we're going to prove that for state Q2, Q2, is that really the one we're doing? Oh, because we got to go this way too. All right, let's just go through and do it. All right, here, and I got my beautiful lines. Right? Don't you love my lines? All right, so here, if it's in there, then this has a path of length t plus 1 to Q2. Right? How do we do that? It's just the definition of M. Right? So holler if you don't follow a step. Here, well, if it has a path of length t plus 1 to q, we look at the edges of the machine, and we know that alpha, well, look at the machine. It has 3 types of edges. That's probably why I chose it. Right? 3 types of edges. Has an edge coming from 1, an edge coming from, let's call it 0, and an edge coming from 3. Right? And each one has a different C. Right? So what do we know? Alpha has a path of length 1 to Q1 and C is B, or to Q3 and C is A. Oh, here's a puzzle. Why did I not talk about Q0? Yeah, it's the empty string, and I'm assuming my string is at least t plus 1, right? I'm assuming C is a character, right? So I got off the hook. Everybody good with that? Or I could have cheated a little bit, or I could have gone on and said, or Q0 in C is really the empty string, right? I could have done that too. It's all, I personally would mark it fine either way, right? Okay, here we go. Oh, let's push the button because it's so much fun. All right, here, right, we got that. And hence, right, again, back to the definition of M, right? Definition of M, alpha is in the M of Q1, or alpha is in the M of Q3, right? And then we go another step. Well, now, this is the big one. We're using induction. By induction, that means these sets are the same because alpha is of length t. So alpha is in the L of Q1, or the alpha is in the L of Q3. Right? Everybody following here? We do it again. Now, we're just using our definitions up there, the definitions of L. Alpha, if it's in Q1, is any string, and C is a B. Or, in Q3, it ends in a block of A's of odd length, right? And C's an A. Right? It's just translating down. All right, so that was just translating down. And now we look at each piece. Well, if it's any string and ends in a B, then what do we got? It's any string ending in a B. And here, if it's any string of blocks of odd length and we get an A, then what do we got? We got a non-zero block. Oh, zero here by means non-empty, not zeros. Right? An empty block of A's of even length, right? We had a block of odd length, now we have a block of even length. right? So we got that, and then we go one more step, and we say, well, it's this or this. This is a non-zero block of even length, or, oh, it's an even block of zero length. So we combine it, right? And we keep going. We get that it ends in a block of A's, which is even or zero or even length, right? And then we go one more, and that, by the definition of L, it's in Q2. Everybody got that? And it seems a little hard, but wouldn't you kind of agree that if you're doing it somewhere in your brain, you need to know this, right? We're just formalizing what your brain needs to be doing. Yeah? Yes. Yes. Yeah, this? Yes. Not that I'm telling you what's on the test, but yes. All right? And people would ask that question already, and I kind of gave that answer already. What are the other little things I said? Well, you're only going to have to do it for one state because we only have so much time, right? I kind of said that already. Everybody got what we're doing? Right? I mean, how is the question going to go? Either I give you a machine or I give you a description of the language and you build a machine, and then somebody has to come up with these, and somehow you come up with all of these, and then you do this little proof. And I think it's pretty natural proof. Right? Yeah? Uh-huh.
Can you replace it with saying like bases and L of Q1 compared with B? Like replace it rather than just writing a string every time?
Yeah, well, at some point, to do the proof, you have to get the meaning, concatenate in the string back to meaning. Right? I mean, if I was debating about making you do the things which says that what is the language of Q2? Well, it's the language of Q what? What do we go into first? Q1 concatenated with a B union with the language of Q0 of Q3 concatenated with an A, right? So I don't know. I didn't really know which. So the way I have it written up in various places is well, you could prove this, and how do you prove this? Well, you have to translate them into meaning, do the concatenation, translate it back into symbols, right? And then, how do you prove this? Well, when you go through this, you have to use the fact that you've done this. And I just felt, if you look at this written up, I did it both ways. And what am I you're going to do in a test when you only have half an hour? Right? This doing 2 steps seemed to be too much. So let's just do it straight like this. Right? Does that seem reasonable? And I just figure if I put too much universal statements like this, right, there's some of people who are going to get even more lost. Right? This seems pretty straightforward. Right? And if I was marking it and you skipped a couple steps here because they seem obvious, I'm not going to get too upset, right? If you only skip obvious ones, right? What is an obvious one, right? I don't know. In my test that I did, my example I did before, I kind of went from here all the way down to here in one step, right? Anyway, that's the game, right? This is what you were asking for, more the general connection. I think this is too much for us right now, right? And here, right? So here, dealing with empty strings. Oh, here we're going through, dealing with the proof in the general case. And let's just not go there, right? What else do we do? Oh, here is establishing the loop invariant. I don't know. I think we've done enough of this. I've done the parts that I need you to know. Here, suppose I ask you then to give me a different DFA that does the same thing, right? And here's a different DFA. Why? Well, here, it's all about the meanings of the state, right? Here, what's the meaning? The length of the last A block is even or empty, right? Whenever that's true, we're going to be here. The length of the last A block has length odd, right? Oh, no, the length here, the last block. Oh, here. Oh, we got to be more precise, right? There might be a B block, but the last block of A's is either even or 0. Here, the last block, last block of A's, here, it does end in A's, right? Does it end in A's? Yeah, here. Oh, yeah. So in both of these, the last block of A's is odd. In these, we're still in the A block, and here we're doing B's. Right? Everybody follow that? And then can you see that it gets it? Right? Everybody see these definitions? Right? Because I'm empty, so and here, how many A's have I gotten? Well, you can put B's in between, but after getting a B's, you better have an even number of A's. Right? You can get a B, then you have an even number of A's. And then what over here? Well, I've ended in an even number of A's, so I can do B's, but then I come back and get an A. Oh, and when I'm over here, the number of A's is odd. Right? Here, the number of A's is odd. If I come over here, I get a bunch of B's, and then when I get a new A, well, I got new A's, but the length of the A's is odd. How many people, let's do a survey, an honest survey here. How many people understand this? How many people don't understand it? You don't understand it? Well, let's do some concrete examples. The first one is empty, or it's an even block of A's, or it has a bunch of B's in it and then has an even block of A's, or has a bunch of B's and the block of A's is empty. Right? That's our first guy. What's our second guy? It ends with A's. So you got a bunch of things. And, in fact, what's before could either be a B or nothing. And then you have an even number of A's. An odd number of A's, right, which means it's not 0.
Okay, so the last block should be block of A.
And then this last state says that we have B's, but if you look at the previous block of A's, it's odd length. Right? Everybody see our 3 different meanings here? And now, you get the meanings? Okay, now how do we go from now there's 2 directions you can go, right? You can say, I have these meanings I have to put in the edges. Right? So it's kind of induction from T to 2, you assume you go from T to T plus 1, which is kind of backwards. You're supposed to go from T plus 1 down to T. Right? But here, let's say I'm over here. So suppose I'm here and I get an A. Right? In all of these cases, if I get an A, I got one of these. Right? Isn't that true? Because suddenly, right, and here we could have, it's an odd, right? So I could have 1A. Right? So if I'm here and I get an A, I go over there. Right? But if I'm here and I get a B, I'm back here. Right? Now if I'm here and I get an A, then I'm over here. right? Now, if I'm here and I get a B, then I'm over here, right? Now, if I'm over here and I get another B, I'm still over here. If I'm over here and I get an A, then what have I got? Something up to B's or nothing, followed by an odd number of A's. Well, 1 is odd. Right? Does that make sense? So you can see how I hope that this example, in fact, proves everything I'm trying to explain. That if you get nice meanings here, then by induction, you can say, if I'm here, then I go here. Or maybe we could do it the other way. Suppose I had a path of length t plus 1 and I was here. Well, then what was my previous t? It must have been this or it must have been this. Right? Everybody kind of follow that? Are you good?
Yeah, I think I understand that part. But I have a question. I know I asked you yesterday about it, but can you point exactly what makes a DFA different from an FA? Because like the only difference is, I see from the beginning, is like instead of having the AB in the circle around, you only have the B.
All right. So this one here, I would say, is only pseudo in non-deterministic because it's not so hard to fix it, right? In fact, we fix it like this. But when is it really bad? If I have a state and there's an edge going 0 here and an edge going 0 here, that's hard to fix, right? So this is very NFA, right? This epsilon we could fix. These lack of B's, which one has a lack? This one has an A, this one doesn't have a B coming out, right? So if you get a B at this point, you go to the dead state. Yeah? No. Determinism, right? We've got to read some Descartes here, right? If you know the state of the universe right now, here's a question that Descartes asked. Newton claims that if you know what every atom in the universe, where it is and where it's going, then you can determine, using Newton's laws, what's going to be true an hour from now. Right? That's determinism. Right? As opposed to non-determinism is you have free will. Right? So here, this machine is deterministic. Because if you know what state you're in and you know what inputs are coming to you, then you know exactly where you're going to be. Well, this one's non-deterministic. If I get a B, I either can come down here or I could spin around. Right? Are we done, guys? All right, I hate to tell you this, we still haven't covered everything that's on the test. So be sure to come to next class.